Welcome back. So this is one of our first lectures on probability in this series on probability and statistics. And so I'm going to start off really simple with just defining what is a probability, giving some really simple examples with things like coin flips and dice roll. And then I'm going to give you some idea of how probabilities can be used in much more complicated tasks in the real world. Things like modeling the likelihood of, part failures or hurricanes or, things like that. Okay? So at the very simplest, probabilities are how we calculate how likely some event is to happen. So the probability of an event A. Now I'm going to define what I mean. So an event A could be if I flip 2 coins, the event A could be that I get no heads. So what's the probability of an event happening? The probability, I'm going to try to color code here if I can. The probability of A happening is the number of ways that this event can occur, number of ways A can happen, divided by the total number of things that could happen, period. Divided by the total number of things that can happen, like the total number of things that can happen. So I'm going to give you some really simple examples with coin flips and dice roll, but very soon we're going to start computing the probabilities of pretty sophisticated things. We're going to compute the probabilities of, what's the probability I get a straight flush in poker? What's the probability that if I have a triple redundancy system, I could still have a failure on a critical system? What's the probability that if I have a positive test or a symptom that I actually have the disease? Okay, these are the kinds of things we actually want to compute the probabilities of, and we'll get to those very quickly, but let's start with some really simple examples. Okay, so let's start with coin flips. That's super easy. I have an actual coin right here. This is a Washington State quarter. It has Mount Rainier and a salmon on it, and I can flip this quarter 2 times. Okay, I got a tails the first time, and I got a heads the second time. Okay, so this is a fair coin. I actually shaved this morning, so you wouldn't second guess whether or not my coin is fair. So let's just set up a problem. Okay, so the example is I flip a coin twice. Now, 2 questions I could very easily ask are, what is the probability that I get, what's the probability I have at least 1 heads? So let's say that my event A is at least 1 of these coin flips turns up heads. And 2, I could say, what's the probability? So another event B could be, what's the probability that there are no heads at all? Probability of no heads at all, period, out of the 2 coin flips. So this is super easy to compute, and I think any of us school kids, right, could compute this pretty easily. But I'm going to formally do it so that we see that it really is just about fancy counting. Okay, and then we'll do a more sophisticated example, and then we'll zoom out. So the first thing I'm going to do is I'm going to compute this denominator here. What is the total set of things that could happen, period? So if I flip a coin twice, the things that could happen, I could get, maybe I'll do this in orange. I could get heads and then heads. I could get heads and then tails. I could get tails and then heads. Or I could get tails and then tails. This is the set of all things that could happen. And we're going to just give this set a name. We're going to call it omega. For right now, you don't have to worry about set theory, but very soon we're going to need to start defining what is a set and some set theory to do more sophisticated probability. But for now, let's just say this is kind of a collection of all of the things that could happen as omega. There's 4 things that could happen. So this denominator is 4. Now, A being at least one heads, what are the set of coin flips where at least one of the coins was heads? So now A is the set heads, heads, one of those is a head, heads, tails, and tails, heads, but not tails, tails. Neither of those are heads, so it doesn't satisfy event A occurring. And so the probability of A is the number of ways A can happen, there's 3 ways A can happen, divided by the total number of things that can happen. So 3/4 of the events have at least one heads, or 75%. Okay, so that's really, really simple, and I'm just kind of codifying what you already know about basic probability. And one of the things I love about probability is that, all of our favorite games, darts and backgammon, poker, dice, D&D, all of them, they have some element of randomness, of probability, and you can actually calculate the probabilities and get better at winning those games. So that's kind of fun. Okay, what's the probability that there are no heads? Well, so this set B, there's only one element in this set, and that's if I flip 2 tails. That's the only way I can have, I don't get at least one head, is if both of the coins are tails. And that means there's only one way that B can happen. So the probability of B is 1 in 4, or 25%. Okay, really easy to compute these. But for example, what if I flip 1,000 coins? What's the probability that I get 300 heads? That would be a huge pain to count all of the possible ways I could get 1,000 coins flipped and then, add those all up. So we're going to very, very quickly come up with formulas and models and better ways, clever ways of counting these probabilities. That's all probability is at the end of the day, is just clever ways of counting how many ways that thing can happen out of the total number of things that can happen. This is actually, also how we define entropy in statistical mechanics. It's how we think about, the theory of gases and gas dynamics. It's actually a very, very big idea. I'm just showing you some baby examples right now, okay, to make us feel comfortable. Good. Maybe I'll do one more example and then we'll zoom out. So second example is pretty easy. So my second example is, let's say I roll 2 dice. Okay, I roll 2 dice. Now, depending on who my audience is, I have to specify that this is a 6-sided dice with equal probabilities. Okay, again, I'm making assumptions here, and you need to be defining those assumptions if you want to be really careful. This was a fair coin, and each of these flips was independent, meaning the second flip had nothing to do with the first flip. This is a fair 6-sided dice, and each roll is independent, meaning the 2 dice don't affect each other. Now that isn't always the case, but it's the easiest set of assumptions. So some of my questions I can ask would be things like, what is the probability that at least one of these dice is a 5? The probability at least one die is a 5. Okay, I'm like running out of space here, but what's the probability that at least one die is a 5? There's a lot of ways of solving this. The kind of most simple, foolproof way, and it's not the best way, but the simplest way would be just list all of the possible combinations. How many possible ways can I roll 2 dice? Well, the set of all dice rolls, I could get a 1 on the first die and a 1 on the second. 1 and 2, a 1 on the first die and a 3 on the second, a 1 on the first die, 4 on the second, and so on and so forth. ... I could get a 5 on the first die and a 2 on the second, a 5 on the first die and a 3 on the second, ... And eventually, if I enumerate all of them, the last one would be a 6 on the first die and a 6 on the second. And it's pretty easy to compute, just with kind of basic arithmetic, that there are 36 total things that can happen if I roll 2 dice. The first one, there's 6 possible dice rolls, and the second dice, there's 6 other unique dice rolls for that dice. And so there's 6 times 6, or 36 possible things that could happen. So now I want to count how many things can happen so that I get at least one dice is a 5. And I'm just going to go through it, even though it's a little boring and you know how to do this, just to remind you that I'm just going to take out of all of the things that can happen, all of the cases that satisfy this condition of at least one of the die being a 5. Okay, so if the first die is a 1, the second die has to be a 5. If the first die is a 2, the second die has to be a 5. 3, 5, 4, 5. Here's where it gets interesting. If the first die is a 5, the second die can be anything. 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6. And then again, if the first die is a 6, the second die has to be a 5 for at least one of them to be a 5. And if I count this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, the probability of A occurring is 11 out of 36. So just under 1 in 3 chances of getting at least one die being a 5. So that's pretty easy. Now again, if I wanted to compute the probability, if I rolled, 15 die, what's the probability of at least 3 of them being 5? That would be very hard to compute using this counting method. The counting method is it's like counting on your fingers. You don't actually want to do it, but you can always fall back on it as a thought experiment. That's how you can always count that way. Another way to do this would be, I could draw a picture. I could say, well, I have 6 possibilities for the first die, and then for each of those, I have 6 more possible outcomes. So each of these, if I drew it correctly, would have, 6 more, and I could count that way. That's another way to do it. Maybe a slightly better way to do it would be to say, to actually try to reason through the ways these could happen. I could say the probability of A is equal to the probability that the die 1 equals a 5, plus the probability die 1 doesn't equal 5, times the probability that die 2 equals 5. So either die 1 is 5, and if the first die is not a 5, die 2 has to be a 5. And I can compute this pretty easily. The probability that the first die is a 5 is 1 in 6. The probability that the first die is not a 5 is 5 in 6. There's 5 ways that it cannot be a 5. Times the probability that the second die is a 5, that's 1 in 6. And if I add these up, I get 6 over 36 plus 5 over 36 is 11 over 36. This is a slightly better way of calculating this without listing all of the possibilities, ad nauseum. Good. Okay, so really, really simple. Let's zoom out. Probability is one of the most important ways we model the real world. We model weather probabilistically. We model health outcomes probabilistically. We understand the likelihood of having cancer given symptom X as a probability. We build probabilistic models of part failures and manufacturing outcomes and safety outcomes. What is the probability that my self-driving car is going to hit a pedestrian? What are the probabilities that some critical component is going to fail, while I'm driving or in midair, or et cetera, et cetera, et cetera. Those are probabilities that we're computing, and we want to model those. At the end of the day, you calculate how many ways that thing can happen divided by how many total things can happen. That's the simplest way to think about probability. But again, zooming out, I made some big assumptions here. In these cases, the probability of a head or a tail, those are equal probabilities. The probability of, all of the dice rolls, it's a fair dice. So 1 is as likely as 2, is as likely as 3, and so on and so forth. So we'll get into cases where there are, not these kind of uniform probabilities of things happening. We'll also get into cases where the probability of sequential events is not independent, where future things will depend on past things. That's interesting too. There's this interesting idea that this coin is random. We haven't really talked about what we mean by random. Random is essentially this idea that the outcome of this coin flip is not deterministic or is very hard to model deterministically, meaning we have to build a probability model for the outcome of this coin flip. It's a little circular, but if you think about it, flipping this coin actually is deterministic. It's a physical coin. It has mass. It's not, quantum mechanical. When I flip this coin, there's wind resistance, there's mass, there's inertia. It's acting under the effect of gravity. It is a predictable deterministic system. There is, a formula essentially for the physics of this coin, and you could simulate coin flips. What we mean by random is that the outcome of this coin flip is too hard for me to predict with the information I have. So for me, it might as well be random. It might as well be a 50-50 chance. Now, it's interesting, in the machine learning era, I actually bet you could take a video of me flipping a coin, and if you had enough information, you could probably predict what the outcome is going to be better than coin flip, better than 50-50 odds from the information of that coin rising to its peak. I bet by the time you see it go up to its peak, you could call it in the air, heads or tails, with the machine learning algorithm. That might be a cool project to try to build, actually build a classifier to see if you can tell, what the coin flip is going to be in the air just from watching it flip, okay? Maybe you could, maybe you couldn't, I don't know. I can't, and so for me, it's a random event. There's a probability associated with it. And that's how most of the world is. Weather is deterministic. There's physics that drives the climate, that drives the weather, that drives clouds and storms and tornadoes and hurricanes. But with the information we have, with the uncertainty in our measurements and the uncertainty in our information, at some point in the future, all we can say are probabilistic estimates and probabilistic forecasts. The better we measure and the better we model those physical systems, the tighter those probabilistic estimates become, and eventually they might become deterministic. We might be certain that this is going to be a heads just from observing its path in the air. But with increased uncertainty, things look more and more random. Now, some things truly are random. The decay of a radioactive element, that's actually random. That is a stochastic process. It's kind of a quantum mechanical process that is truly random. So radioactive decay is an actual random process. But a lot of the things that we pretend are random are actually deterministic. They're just too complicated for us to actually understand and model, and so we model them with probabilities instead. It's a very, very useful way to model things like turbulence. If I think about the molecules of gas in this room, I can't model every single atom, and I don't want to. I model the average value of their velocities, and I call it a temperature. That's a probabilistic or a statistical way of quantifying information. I guess parting thought here, very, very important. We're going to get to this soon. Probability is all about modeling what can happen and counting what can happen. Statistics is almost the inverse problem. Let's say I flip a coin 10 times and I get 10 heads in a row. What are the chances that that coin is fair? That's a statistics problem. So I have a model of what I think the coin is behaving like, but then I actually collect data and it might disagree with my model. What are the chances that that is truly just from the randomness, the natural randomness of the system? And what are the chances that my coin, my model of the coin, are wrong? So that's what statistics is all about. Is hypothesis testing, testing your probability model, collecting data, and making hypotheses about that, or inferring things. If I measure certain genes or certain health traits, can I infer what is the likelihood of some underlying causal effect, some underlying disease that's causing those symptoms, that's causing those test scores. So those are all things that we're going to talk about soon in probability and statistics. We're going to start with real simple examples. Very quickly, we're going to learn how to calculate much more sophisticated things like poker hands, probability of part failures, how many parts you need to inspect to be 99% sure of a certain quality or a certain reliability, things like that. Tons more coming. This is one of the most powerful, useful ways of modeling the world. We're going to question our assumptions. We're going to try lots of things. We're going to build lots of probability models. And soon we're actually going to start collecting data and running experiments and doing statistics against these probabilistic models. Okay, thank you.